circuits that are used and that do most of the interesting stuff in the processors, so that we can have at least a bit of an idea of what or why we were actually talking about these things. Next week, we will continue with sequential circuits. So we are again going to go take a few steps back, do a bit of, let's say, more regular stuff, boring stuff, okay? But then progressively we will get more, or I hope it will get more and more entertaining and exciting. And then you will also realize the things that we are talking about are things that make up processors and digital circuits. So today is the first part. And if I can manage to help. Yeah. So what we are today going to talk about are arithmetic circuits. And we want to, or I have a deep passion for multiplexers, you know that, but also for adders. So those are my two loves. And today I'm going to talk about arithmetic circuits. We say they are important. And then we will spend most of our time discussing about adders. Circuits that add two binary numbers together. Very exciting. And we will see two binary numbers, more than two binary numbers. But it's not only addition. You will see that most of the interesting operations will be done one way or another by basing the functionality on an adder. We might enhance it a little bit. We might play around with a little bit. So making good adders helps you make more or less everything else. We will see this in multipliers, and then we have like 5 slides talking about things that do not use adders. There are very few. And having them alone is probably not so much interesting. What we are trying to bring this story to a close is bringing to something that we call an arithmetic logic unit, which is actually the heart of every processor, of every interesting digital circuit. So more or less, if you are doing a digital design that you want to show off and say, hey, this is a great digital design, I love it, I like it, it's so great, so fast, calculates so many things. The heart of all these operations will be the arithmetic parts that do the calculation. Everything else in the circuit is essentially a side dish. It's there so that the arithmetic logic units can add, subtract, multiply, manipulate those numbers in great efficiency. In most cases, the performance of the system will be determined by how efficient you can do these additions, subtractions, multiplications. So whatever the clock rate, the speed, the area of the circuit is, of these arithmetic circuits is going to play a major role in our system. So if you can optimize the arithmetic circuits, this is how you go forward. So for those of you who are interested in, let's say, machine learning and AI algorithms, one of the hot topics today is quantization. Anybody hear about that? Quantization? Okay, some people using brain floats, B floats. Anyone? Okay. In the core of the idea is they want to get faster, better, more efficient, and they realize operating on larger numbers takes a lot of time, a lot of area. So one solution is, can I not operate on smaller numbers? Can I not operate on 8 bits, 4 bits, 2 bits, a single bit? So this is one of the trends. This is driving the research at the moment. And you will quickly understand why this is happening. And there is a lot of fun improvements come in finding newer and better ways of combining and making arithmetic calculations in these circuits. And any improvement you have here is directly going to improve the circuit. So it's an exciting place to work in. Now, I didn't update this slide very often. So this is an older ARM processor. And this is one of the most popular embedded microcontrollers, but essentially the style is not so much different from MIPS, which we are going to study, or RISC-V, which is very popular these days. And if you look around, not very carefully, but like superficially. First of all, you're going to see my love of my life, you know, multiplexer, multiplexer here, multiplexer, 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 multiplexer. It's everywhere. It actually helps you direct the data from different sources. You can select, am I going to do this or this? And then the rest of it, if you look here, you see a multiplier. This is an accumulator sort of thing, a shifter, an arithmetic logic unit. There are other things that look like they do something crazy, like DINC. It's an incrementer. And saturation unit, they all have additions, subtractions, and other arithmetic operations inside. So if you look inside the core of a processor, most of the things that you will see will be some arithmetic operations. And if you look at the instruction set, this is a simplified core ARM instruction set, and you see all these different types of operations, you can identify the most exciting ones. They all rely on arithmetic circuits one way or the other. The rest, what does the rest do? Any idea? It's quite boring, processors inside. So this side, sorry. Nothing? Yes, that counts, right? I mean, it's just right in the middle, yeah. Yes. Most of the others is moving data from memory to somewhere, moves things back and forth. It's just data manipulation. Data is here, data should go there. Data is here, it should go somewhere else. And then there are some exceptions and some other things. Hiding there are also like AND or XOR, which are logic operations we discussed about. So once you actually are through this lecture, you will see most of the exciting operations that the processor can do. And that's scary. It's just a Friday afternoon, an hour and a half, and we will already have most of it. So type of arithmetic circuits in terms of complexity in realizing them in digital circuits looks roughly like this. So the very, very simple things which if you are programming, maybe not so obvious, are things like shifting and rotating are the easiest things for us to do. Then comes comparison, increments, negations, additions, multiplication. And now the rest gets slightly more problematic: division, square root, exponentiation, trigonometric functions or logarithmic functions. Those are challenging to implement in digital hardware. We usually will, in a lot of cases, we will take advantage of software programmed solutions to help us implement them. Sometimes they will be implemented in hardware. Sometimes we will use iterative algorithms and make use of the rest of the things a number of times to calculate them. Now, there is one slide that I like a lot. It has the same complexity analysis here, if you want. And as a center point, there's an adder subtractor. And what you see here is the same functions I talked about, but shows their relations. So the adder subtractor, negation, increment, decrement, and compare are actually closely related. So you take an adder and you realize it's not the complex form. You take things away and you end up with these things. And then the multiplication requires shifts and adds. Square root requires adders, shifters, and comparisons. Division the same way requires adders and comparisons, etc., all the way until you come to logarithmic trigonometric operations. Trust me, I'll try to convince you throughout the lecture, the adder subtractor is the main interesting operation that we are looking at. So we will spend considerable time trying to add numbers, and we start with baby steps. So first, we want to add 1-bit numbers. So number can only be 0 or 1. Essentially, what I'll be doing is I'll be counting bits. I have a circuit who has 2, 3, 4 inputs, and I want to see how many of my inputs are 1. I'm counting the number of ones. Now, once I manage it, I will go and try to say, hey, 1 bit, I do it now, but I want to learn how I can do more. So I want to add 2 numbers that consist of multiple bits. 2 bits, 4 bits, 8 bits, 64 bits. We will realize there's a very easy way going it. And then we will go and say, hey, We want to be able to use different circuits based on adders that do different things. And then, hey, I know how to add two numbers. And now you'll say, Frank, this is trivial, right? If you can add two numbers, you can add a third one to it, and a fourth one, and a fifth one. However, there will be an issue adding two numbers. There's a curse involved. Because of that curse, we want to optimize this thing, and adding multiple numbers, we will use some nasty tricks. Nasty tricks means you can ask in exam questions. Okay? Great. Are we ready? Okay, let's go. Now, this is your first connection to the previous lecture. We want to do a half adder. In other words, a 2 to 2 counter. Why do we say 2 to 2? Because I have two inputs, A and B, and my outputs will be S and CO. S for sum, CO for carry out. And this is the basic operation. And since I have only two inputs, what I can do and what I should do always is to make a small truth table. Because, you know, two inputs can have only 4 possibilities. That's the extent of this circuit. You're already trembling in excitement, I see. So 0, if I add 0 to 0, the sum will be 0. There will be no carry out. If I add 0 to 1, the sum will be 1, no carry out. If I add 1 to 0, well, sum is still 1, no carry out. And now comes the exciting part. If I add 1 to 1, the sum will be 0, and I will have a carry out. And if you read the number here, 0, 1, 1, 2, right? So taken together. Questions so far? Yeah. Why is it called counting? Because, you know, you are counting how many bits here are 1. I mean, if I had 30 here, you know, and if I somehow scaled this guy, and then you're just asking, hey, there are 30 connections, how many of them are 1? You don't care if the left one is 1 or the right one is 1. You're not giving them any ranking based on where they are. Each bit is equal here. Yes. Did you just move from here to here, or that's a real distribution?
Why do you call it half adder? Why is it half?
Because the next slide is going to introduce a full adder. And this is half of the story. It's a half of a full adder. So this is the half one. It's a stigmatized adder, I know. Okay. Question? No. No, it's just bored. Okay. Okay. Now, next slide. That thing that you anticipated with a lot of time is the full... there is this thing blocking your view. Sorry. No, I cannot. Believe me, it's full. Half. I have no idea how to remove it. If some... Oh, no. Okay, that it's not that important. After the break. We're not waiting 5 minutes to remove that guy. Okay, full adder. So full adder is the essential block. We started simple. We said, we have a half adder and things, and it was very easy to explain. Now the full adder adds another input. So I have 3 inputs, A, B, and the carry in. It makes sense because if I have a carry out, then I should also have a carry in. So maybe I can make nice chains of these things. So this person now can add 3 one-bit numbers. So it can count its input, 3 of its inputs. And this one is such an interesting thing. People go crazy. So if you're in electrical engineering and lived in the 80s, you would be going crazy trying to implement. Remember the transistor level descriptions we said? So there's a very classical way of implementing it. But because it's so interesting and so frequently used, people try to optimize it even further. They came up with very, very exciting ideas. You don't care about it so much, but significant effort went into making full adders even better than they are. And since this will be one of our cutest building blocks, making it better, making, for example, the time it takes from A, B, C, I to S or CO, you know, the delays, making it faster, making it smaller, will be one of our prime goals. Is it possible to write its truth table? Sure, we can, but it's not something you would be surprised to find out, right? So if all of its inputs are 0, these guys are 0. If A, B, or CI is 1, sum is 1, CO is 0. If AB, BC, AC is 1, S is 0, CO is 1. And if all of them are 1, yeah, both the carry out and the sum is 1. Logic? Great. I love the positivity. Now that we added 3 numbers, we say, can we add 4? Can we add 5? Can we add 6? I mean, let's go. Let's make even more. And now all of a sudden, we will see we can do it in a couple of different ways. Here you are. Now, I want to add A0, A1, A2, A3, A4, A5, A6. These are all 1-bit numbers. And I have 2 different ways of doing it. This one is a linear structure. I say, okay, the top one is going to add A6, A5, A4. This is the sum. This is the carry out. To this guy, I will add A3 and A2. He will create a sum and another carry out. And to this guy, I'm going to add A1, A0. And this is the sum, the least significant bit. This carry goes here. I have 1, 2, 3 carries, so that generates a sum. And the carry comes out here. So I have 7 inputs and 3 outputs. And not surprisingly, I can actually, with these 3 bits, represent all numbers between 0 and 7. Right? Yay! Excited. And I can do this then for any number, you know, give me any number of bits. By combining the full adders in a, let's say, smart way, I can do this. And now look at this. So this is calculating the least significant bit, the sum 0. This one is calculating the next significant bit, the sum 1. And the carry out will be the sum 2. So there is a hierarchy, right? The carry out has a higher value. It's 2 times more than the sum bit it produces. Now, we looked at this. And then we realized there's also this version. And if you examine it a little bit, it's not like we have to memorize it, but you see that we do some parallelization. The first full adder sums up A6, A5, A4, and the second one sums up A3, A2, A1. We generate the sum here, and we have A0, we add that, so that's my least significant bit, and the same carryouts come here, and I add them up. They both will do the same. Do we agree? Yes? Good. Which one is better? Ha. Okay.
I think the one with the tree structure probably has a lower propagation time because it has like less steps.
Yes. So that's a very good observation. This one seems to have an advantage because from the inputs, if all inputs appear at the same time, all inputs are there at time 0. And if all of these units are the same, which they are, right, full adders, and let's say the calculation, the time it requires for this full adder to propagate from the input to the output is, let's say, unit delay. In this case, I have 1 delay over this guy, the second delay, and then the third delay. The red arrow shows you how much time it takes. So this organization of the addition of multiple bits takes 3 steps. This one, 1, 2, 3, 4. 4 steps. So one of them is 33% faster than the other. Right? This one runs 4 gigahertz, this one runs 3 gigahertz. Okay? So shall I mean, this is our favorite. Who likes this one? I mean, what did I say about diversity just like the beginning of the... This one? A little bit forced, yes. Not many people like this. What do you think, I mean, for those of you who like it, what do you think is the advantage of this thing? Yeah?
Maybe because the wires don't cross.
Okay, that's actually not a bad idea, but there's something that causes the wires not to cross. Yeah?
Feasibility, much context that makes sense. It's easier to understand if one would like read it.
Okay, so easy to understand, yeah? Why?
Yeah, because like the structure gets more and more complicated,
The more?
like if we don't just use A0 to A6, but I don't know, say A0 to
A540.
yeah, like you want to add a lot of numbers, then like the tree structure gets very, I guess, complicated.
And this one is, there's one word that we use for this. Yeah? Yeah, but this one is, when you say, this one is complex, this one is modular. Who says regular? There is a simple regularity because at every level you are adding another 2 in. You know, you could go down, and the way to construct it is actually simpler. Here, when you want to go from, I don't know, 6 to 15, 7 to 15, you will realize that it's a funny iterative structure. It is possible, and what your colleague was saying was correct. There is a bit of funny things going here and here. It's not immediately, easily replicatable. Both are used, both have their advantages and disadvantages, and this is what we will be dealing all the time in digital logic circuits. There are very few obvious winners. There will be always a trade-off between one quality of the circuit and another quality. In this case, regularity will allow us to implement this more easily, make a physical circuit with shorter wires or a more regular placement on a two-dimensional surface. Whereas this one has a speed advantage because we don't have that many levels of logic going through, definitive plus. But it brings in a complexity in the way things are connected, in the way things are scaling. Doesn't mean that one is good, one is bad. Both of them have their uses. Both of them will be used under different circumstances. It will depend what you value more in your design. Is it scalability? Is it speed? Sometimes you will sell out for speed. You will say, take me, take anything, just make the circuit faster. And sometimes it will be power, say anything, but I want to save every single electron I can, and I don't care about the speed. It has to have little power consumption. So we did the very exciting task of adding single bit numbers, and even if we have 500 of those, with a little bit of, combination of these things, we will hopefully manage it. Or at least you will manage it in an exam. Yeah, what? What did he say? Okay, now we want to go to multiple digits because, counting sheep, counting bits is not the most exciting stuff. So we are trying to, again, liken this to decimal addition. How does it work? We said 8 plus 7 makes 15. There's a carry. It goes over. Oh, I have a slide. Okay, I'll show the slide later. And then we add here, so I have a carry 1. 1 plus 1 plus 3 makes 5. No carry. 9 plus 4 makes 13. The carry goes over here. Binary addition will be exactly the same. So I have a binary number. I have no idea what this is. Big number of zeros and ones. And I'm adding it to another big number of zeros and ones. And 0 plus 1 makes 1, 1 plus 0 makes 1, 1 plus 1 makes 2. So there's a 0 here, 1 carries over, 1 plus 0 plus 1. Then. Let's skip the slide before I make embarrassing mistakes. So this is how it works. 1 plus 1, the carry goes over, 1 plus 1, carry goes over. 1 plus 1 makes, again, carry goes over, and then we sum them up regularly. Simples? Okay. When does it get exciting? Well, we can talk about how we can realize these things. And the best adder, or the simplest adder, it's best because it's simple, is what we call the ripple carry adder. The zoom screen carry adder. Okay, there's a ripple there. Go away. All right. Now, the ripple carry adder is one of the mainstays of arithmetic operations. First of all, because it's very simple. You define a ripple carry adder of arbitrary bit length like this. You have two vectors, A and B entering. You may have a single bit, a carry in, entering to this adder from the right side. And it will calculate a sum that is equal to the length of the input vectors. And in addition, it will create a carry out in case this addition results in a number that cannot be expressed in the length of S. And now once you zoom in into this, we can go back and take our beloved full adder, the one that, you know, was so boring. And you realize I can take a full adder. This is the carry in that I was talking here. I take A0, B0, so the 0th bit of the vector A and the 0th bit of the vector B, and I calculate the sum. Now, if this sum has a carry, I pass it to the next full adder, which is a carry in, and B1, A1, and I create the sum, and I pass it, and pass it, and pass it. So if I have n bits, 512 bits, right? So A 511, B 511, sum 511, and finally, if this guy still has a carry out, he will spit it out. And that's it. This circuit, this simple full, first of all, we started with a very simple full adder. We realized there's 3 inputs, 2 outputs. So we can write we can make a truth table, use a Carnot map, use our own logic, has 2 outputs, figure out what gates, what ANDs and ORs are needed. So I can do this. You can do this, definitely, 100%. And then you take a bunch of those and string them up together. Question?
Is there a specific usage of this carry in other than incrementing by 1?
There will be a lot of uses of that carry in. But since you are asking this question and somebody was saying, you were saying, right, why is it half adder? If you don't need the carry in, you can save this and turn this into a half adder if there's no carry in coming. Okay? But this is going to be very, 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 very handy. Now, we can sleep easy. We don't have to study any digital electronics, and we can sleep before the weekend because someone is sleeping. So the issue, I mean, we wouldn't have any issues and there wouldn't be any computer architecture kind of digital circuits kind of things if story ended here. But here is the curse. We call it the curse, the zoom screen of the carry, curse of the carry. And the basis of the operation is that the most significant output sum depends all the way to the least significant inputs. This means that the longer I add things, the longer it will take for this circuit to make up its mind. And so it will work, I think, yeah. What I will do is I will come up with 2 numbers, 2 random numbers that I'm making up. Very dangerous, don't do this at home. So we will try to okay, this is the first number. Let's say this is A. And oh my God. So this is A0, A1, A2, A3. Why did I do this? A5, 6, 7, 8, 9, 10, 11, 12 bits. Okay? And then my second number is so Do you remember the binary numbers? So what is the lower number? I hear it. Somebody just 1. What's the upper number? Depends is the right answer, by the way. So, exam question, what is the upper number? Great. So I give you 5 options and which ones are correct? Okay, it's 2000 probably. Okay. If this is representing a positive number, this would be 2047 probably, or 4095. Okay. What else? Yeah. Minus 1023. 24 would be round, right? Aha. In what format are you? Okay, 2's complement. So we are going to do a little experiment. What would be this number in 2's complement? How do I take 2's complement? I have a cheat sheet here. I have 12 times 1, 4, 5, 6, 7, 8, 9, 10, 11, 12. What do? I invert them. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Sorry. And I add 1. So minus 1. If this is 2's complement, we are looking at minus 1. So plus 1 plus minus 1 makes 0. Okay, great. So let's do this binary addition one by one. And you will see what is happening. So first of all, carry in is 0. Okay? So the first full adder takes A0, B0 and says, hey, at the moment when everything, once all these circuits get this number, they get the number at the same time. So there are 12 flip-flops, you know, there's this first guy, second guy, third guy, fourth, fifth, sixth, everyone gets all the inputs at the same time. They look at their inputs. Let's just take this guy. What will he calculate? Well, there is no carry in coming, and he says 1, 0, so the result will be, the sum will be 1, the carry out will be 0. So the carry out is going this way. So he says carry out is 0. The same time, this guy is doing the calculation and says, yeah, the sum is 1. 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 There's no more sum. And the carry out is 0. And these guys the same way. They will say sum is 1, sum is 1, sum is 1, sum is 1, sum is 1. And at the same time, the first step, this guy is going to go, okay, I have 1 plus 1. The result, the sum is 0. And the carry is 1. So he's sending over the carry is 1. Now this guy already finished his calculation. They said, yeah, I added 1 plus 0, carry was 0, so the result is 1. And now it says, hey, excuse me, there's a carry. Really? Okay, I have to work again, and I will calculate it, and now the sum will be 0, and I will send the carry over here. And now the second guy, I mean, he was long gone and done. You know, he's looking forward for the weekend, he's going home, and says, hey, excuse me, carry. Okay, he's going to change his mind and he's going to change the carry, and then. Do you know why they call this thing ripple carry adder? Because the carry ripples through, and in the worst case, as long as this calculation is, it takes that many steps to get the output result correctly. Now, going back to the combinational logic and timing we were talking about, the first time where the output changes is when this input created a result where the result was 0, 1, 1, 1, 1, 1, 1, 1, 1. That was our contamination delay. And after a while, this carry propagation created a massive mess. propagate it back and forth, and everybody's, oh, no, I just finished. Okay, let me do it. Here, take another carry. Are you kidding me? I was, okay, here, take the carry. And then after quite a long while, I mean, if this is a 128-bit adder after 128 time units, this guy will finally say, okay, you know what? The result is 0. Okay? This is what we call the curse of the carry. And this will affect us quite a lot. I don't think I will, just looking at the time, trying to look at the time, I don't think I will finish going to the next set of slides. We will do them, cover them probably sometime else. Just to get rid of this, people have tried to do very, very inventive ways to make adders faster. And the only reason why we are making adders faster is because the simplest adder we can think of, which is a gorgeous adder, is taking too long in the worst case. What I have drawn is the absolute worst case. There are only 2 cases. You know, A is -1, B is 1, or vice versa. In all 2 to the 24 combinations that I could have written here, which is a lot, and they take the longest. There's a lot of additions which can be calculated very fast. It just depends on how much the carry has to be evaluated. And we call these type of adders that have to propagate the carry through carry propagate adders, in short, CPA. Now, any questions? This one is important because we will be building on this thing. Yes? Yeah, I mean, it's a good question. Is there anything, I mean, why do I care about it, right? This operation takes long. So we didn't see it yet, but in the next lectures, we are going to talk about sequential circuits. And in sequential circuits, we are going to divide the operation of our circuit into time units. And we will say at every time unit, at every time step, we want a certain operation to finish, and we will leave enough time for this operation to finish. If it's a processor, we are talking about the clock frequency, meaning how many times I can do a certain operation within 1 second. So if this operation takes long, I have to give enough time within the clock period so that this operation can finish reliably. Because if I want to add these 2 numbers, the result will be 0. The result cannot be -35 or something like that. The result has to be 0. Otherwise, I'm not adding them properly, meaning that if I don't let enough time for this adder to finish, all subsequent operations will be doing something crazy. And it is one of our main problems. Either, you know, we convince people not to care so much about speed. You know, that would be marketing-wise, that would be the best thing. And says, yeah, my computer is too slow, my cell phone is too slow, my AI engine is too slow, and say, yeah, just relax. Why do you need it so fast? Just enjoy the trees and, you know, cows, and let's be all friends, and something like that. That would work. Unfortunately, others may invest a little bit in their digital circuits and create adders that are faster. And while you are advocating for slower circuits, some other company in another part of the country, world, can come up with a solution that's twice as fast and wants to sell it for the same price. And all of a sudden, you don't have customers. And so you say, no, I have to fight against them. And so this creates the entire industry. It's true. Okay. Now, we want to add multiple numbers because we know how to add them. There is this curse situation. And if you have enough time later in the lecture, we can also see how we deal with curses, exorcism of carries and things like that. But let's just take a look at other problems. How can I add multiple adders together. Now the curse really bites us, because if I have one adder and adding these two numbers actually was a fast operation all the way when it came to this propagating the carry. And you say, if I have to add a third number to it, now I have to propagate the carry again. And then if I add a fourth number, I have to propagate the carry again. That's a lot of waiting for the funny carry to move from one side of the numbers to the other side. So you say, can I do it in an other way? And what we will see in a little while is something that we call a carry save adder, which is what a lot of us do, humans. We postpone the problem until it is inevitable, like cleaning up your room, studying for the exam. You know, why study for this lecture now? There is July 20th till July 24th, right? That's when you have to study for the lecture. There's no need to worry about it now. The same way, we are going to use the same principle. We are going to say, look, the problematic part is the carry propagation. Let's not propagate the carry from the beginning. Let's just save the carry. Let's say, okay, I have two vectors. Let's just kick the can down the line. At some point, when I have multiple numbers, if I reduce them, at some point I'll be left with only two numbers, and then, and only then, I'm going to do a real addition. Until then, I'm just going to keep it. Now, the thing that gets very, very complicated, and it's a great exam question all the time, let's not say exam question. This is also a great question for job applications if you are in digital circuits. Ripple carry adders are slow. Ripple carry adders have this like very long propagation that goes through them. However, this slowness works in their advantage when you are adding multiple numbers. When you are adding multiple numbers, you can actually afford to do what I said, let's not do it. You can have the adder at the top is adding the vector A3 and B3, A and B, A3, B3, A2, B2, A1, B1, A0, B0. Now, after he has completed the operation, the second adder adds the vector C, and after that, the third adder adds vector D on top. And this thing works out. You know why this thing works out? Because as the carry is propagating to the other side, this guy is also following suit, and this guy is also following suit. So I don't have to wait until this sum is calculated to start calculating this. The moment that I have the sum here and the C0 here, I can already start going forward. And while I'm doing this, the guy has already decided on the sum, and I can calculate this. And while I'm doing this, A2, B2 has already the carry propagated because it took some time until I came here. And if you look at it, if you only use ripple carry adders, if you only use full adders, and these half adders here, you will realize that the critical path actually goes through the final adder, and then this linear organization of the blocks. You remember the first addition I showed, multi-bits? That's a linear structure. At every stage, I'm adding one more, makes it very regular. And in the end, I have one carry propagation adder coming in here. Let's see, how does it look? Oh, we're already over the time. Let's leave at that. Let's take a break. 15 minutes later, 15 past, let's continue. And then we see what else can we do. Okay, one more lecture, then we can go home. Let's have one last lecture. How great is that? Now, this is, we are trying to add four different numbers. And we realized that by organizing these ripple carry adders, 1, 2, 3 of them, we can actually accomplish this. However, this is a special case. The only reason this works is because this last adder is really slow, because it's a ripple carry adder, right? And while this guy is like slowly propagating, like ta-tang, 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 these guys catch up. So if you are looking at sum 2, any way you can come to it, either this way, or from the middle, or from down here, or from top here, you are crossing 5 flip-flops, 5 full adders. Okay? So the moment that you are calculating S2, one way or the other, all the others will have code up. Okay? Yes?
How do you determine when the adding process is finished? How do you know when you have added something? Because you have to write it.
Yes, which is annoying. It is true. It is part of the, let's say, design process. When you use these tools that generate it, they can analyze the delays, because every one of these blocks has a propagation delay and a contamination delay, and they add up. So you can use a tool which we call static timing analysis, meaning that we are not dynamically changing things given the inputs at some time. He can calculate it, and essentially, when you use a tool, in the end, he's going to say, you know what, you have to wait 4.5 nanoseconds until this circuit finishes. And now usually you're going to say, 4.5 nanoseconds? Are you kidding me? Do something better. Or maybe you'll say, oh, that's great. I wanted 10. It does it in 4.5. I'm super happy. There was another. Okay, now sometimes you are not so thankful. You don't say, hey, I'm glad that it calculates. I don't care how long it takes. Take a day, take 2. Just make sure that these things add up. If you want to have this thing go faster, we are not talking this lecture, or I'll just briefly talk about it. There are ways of fighting the curse. But notice that the moment I make this part faster, then this guy will lag behind. Because I can make this guy go faster, but this S2 will require the input from here. So at that point, I have to make this guy faster as well, and I'll have to make the guy on the top faster as well. So doing all of them faster will require me to make larger, more power-hungry, more costly adders all over the place. We don't like that. So we do the following. We realize that, we realize that if you have a full adder, you take 3 bits, and you generate a sum, and you generate a carry out. If you do not merge these vectors, you can say I have 3 vectors that come in, E, F, G, and I generate 2 vectors, S and C. And I can do this in one step. The moment I have E, F, G available, like one delay of this full adder will generate you the S0 as well as the C0. Notice that I'm not feeding the C0 into the full adder and wait until it propagates all the way. I'm just taking 3 vectors, and 3 vectors become 2. It's a reduction. And I can do it in one single step. So this is what I was talking about. We kick the problem down. So the thing that slows things down is this carry merging with this sum, which potentially generates another carry that merges with this sum, which potentially, so that was the curse. If I'm just saying, you know what, let's save the carry, let's not propagate it, then I can do this in one very fast step. Okay, how does it help me? Well, it helps me because if I want to add multiple vectors, here I have 5. I can use the first carry save adder which does it in one step, reduces a carry and a sum vector. To that I add E, to that I add D, and now I have two numbers. Now I can no longer ignore this problem. Now I have to solve it. And now I put my carry propagate adder at the band. And this one, I can afford to do all my tricks. Whatever I have in my pocket to do something faster, I'm going to take out all the elixirs, all the chanting, whatever. Carry curse disappear. Let's make this faster, okay? Does it sound like fun? Absolutely not. That's why you are studying computer science and not electrical engineering. I know. I'm just trying to explain to you the principles behind it. And this is one of the greater tricks that we use. We kick the problem down all the way until we can no longer ignore it. And at the very, very last possible moment, we say, okay, I did this for a while. Now it is time. Now we have to bite the bullet. Let's calculate the carry. But it saves me from making fast adders all the way. I mean, this could have been 20 numbers, 30 numbers, 60 numbers. I can just reduce them to a level where I bring it down. And notice, this tree structure that I'm building, I could have still made it here, right? At the very, very beginning of the lecture, we were having two different options. And notice that when I'm drawing, I'm usually using the linear structure because it's easier to draw and explain. If I try to put a tree structure here, I would probably confuse a lot of people. I shouldn't make assumptions, but you're okay? Question?
I was wondering why then it's like the header all the way through, like why you still use the same.
Yes.
Why not use all the tricks all the way through?
Because the tricks will cost me. You won't get faster for nothing. So we will have to sell part of our soul, okay, to make this thing faster. We will make it twice as large, 3 times as large. We will consume a lot of power. So we want to say, you know what, let's make one big fat adder, and everything else we reduce it, bring it to this guy, and he'll take care of it. The carry will be sold once. Instead of me trying to propagate the carry here, propagate the carry here, propagate the carry here, being upset that it takes too long, and then making all of them faster adders, it's not necessary. You realize that, hey, I can move things along. Yes?
Doesn't this cost more area?
No. Interestingly, no. Well, if you're using ripple carry adders, but then you are not looking so much. Why are we talking so much about it? Where do you get so many numbers to add? Right? I mean, why are you bothering me? Just add 2 numbers, be done with it. Right? I mean, how can Frank even imagine that we have to come up with adding 35 numbers? It's not like something that happens very often. Right? Wrong. This is why we are looking at it. Multipliers. So in a lot of architectural discussions, people do a lot of things to avoid doing multiplication, because it's known somehow that the multipliers are large blocks. They take a lot of area. They consume a lot of power. They are difficult to do. So people are like, oh, multiplier, no, don't. You know, I'd rather add 5 things, but I don't want to multiply, that kind of thing. So multipliers are known to be large, and they require a lot of calculation. We are not arguing about that, but it's not as bad as you think. It has 3 parts. The first part generates what we call partial products. I'm going to show it in a second. The next part is a carry save tree. Those carry save adders that we said, because those partial products have to be added up. And we will reduce them and then bring one big carry propagate adder to the end and clean up everything. Essentially, most of the multiplier will be one big fat adder and the supporting cast. No question? Let's take a look at the multiplication. So this is the, I mean, between different cultures, I realized that. So this is how I was doing it in my primary school, which was decades ago. It might have changed. But the way I was multiplying at least was that, you start here 3 times 2,417, you write it down. 0 times this, you shift it by 1, you write it down. You write it, and now we are adding it. 1, 5, 10. I have 1, 13, 20, 21, 2, whatever I add, and I come to this number. Is this multiplication scheme familiar? Okay, great. Some people know. Okay. The binary one is exactly the same. Now, we look at it. So I have the number 89 and 55, and I multiply it, and I start from the right. And fortunately, the partial product generation is very easy. Either it's the number itself, or it's all zeros, right? And I shift and I add. So the number itself, the number itself, the number itself, all zeros, the number itself, zeros, zeros. And now I have 1, 2, 3, 4, 5, 6, 7, 8 numbers that I have to add together. And then I'm done with the multiplication. Now, what do I do for the partial product? How do I generate these things? What functionality is needed? Yeah? No. Shifts is, well, I'm shifting them, but how do I come up with the number? It's either the number itself or 0, yes? You could do it because you can do any logic function with a multiplexer, I agree. I mean, it is true, there's no laughing matter, but there's a simpler logic function. And, right? You AND the entire vector with that bit. If it's 1, you get it. If it's 0, 0 and something will be 0. Right? So partial product generation is a sea of AND gates, if you want. And then I have the carry save tree. I have to have these multiple numbers that I have to add. And then I have one final carry propagate adder, and that's it. Remember, it was multiplication. It turned into AND gates and adders, nothing else. So our steps are, for each bit of the multiplier, the partial product is either when 0, all zeros, when 1, the multiplicand, achieved easily by AND gates. Next step, we have to reduce the partial products so that in the end, we have a carry vector and a save and a sum vector. And then I generate the result. The problem is with the multiplications, the way we are shifting and adding things together, if I have an n-bit multiplier and an m-bit multiplicand, the result will be n plus m bits. So 8-bit times 8-bit will give us 16 bits. Okay? And remember what the problem was? The larger the adder, the more we were suffering through the curse of the carry. And guess what? In a multiplier, we end up with a particularly large carry propagation chain. So making the adder faster would pay off that much more here. So how does it look? Let's try a very, very simple one. Now, we have 3 different steps. It's a little bit, looks a little bit weird, but it actually, I'll say it makes sense. No. Okay, let's start. I have A here, A0, A1, A2, A3. I have B, the other number that comes in at the top, and I'm generating the partial products by the blue AND gate. So you can see the B0 times A0 is right there at the top. And then I'm creating A0, B1 and A1, B0. Okay. And then the red guys are my carry save adders. And the last portion here is the one that does the carry propagation at the very end. Okay, now I realize that this drawing, it seems very logical to me, but it's not so logical for everyone. So let me try it here. So I have, let's not make a mistake. It looks like a parallelogram here, right? So I have the A coming here, A0 to A4. I have B coming in from here. So this is B0 times B4. And then there is like the carry propagation coming and generating me the sum. Okay? And now what I'm going to do is, I'm going to straighten this parallelogram. Okay? I'm going to push from here. I'm going to push from here so that this angle becomes like this. I'm like, whoop, pushing this like, ugh. Okay? And this guy will go here. And then this thing that was too much here is going to fold up like this. What are you talking about, Frank? I'm talking about this thing. Ta-da! Okay, it's the same parallelogram as before. I just pushed this way. So the A side straighten up. The B is on the top. And this green side sort of folded around and became like this. Now, this is what is called the parallel multiplier. It's from the 1970s. It's an extremely nice circuit. Can you tell me why I would like this circuit so much? It is easy. Squares are nice, yeah, why not? Yeah. It is very regular and it is very modular. This means that if I want to make it a multiplier of any size, I can easily size it. I'm just, you know, if there is more of B's, I need, this is a slice and this slice repeats. So this slice is the same as this slice. The boundary conditions are different, you know, the ones on the edges, but the ones in the middle are exactly the same. So if I want to make a 32-bit multiplier, I'm just going to add more of these. If I want to have the multiplicand 32-bit, I'm just going to add more rows because guess what? These rows are identical and I can have as many as I want. And all I need to do this are, technically speaking, the AND gate and the full adder. You may notice that here and there's a half adder. Okay, that's not so bad. I mean, I can also use a full adder for a half adder, you know, I mean, or, okay, let's have a full adder, half adder, and an AND gate. I mean, these are the, there's just two half adders here, another one here and here. It's the boundary cases, yes?
For instance, do we have multiple different, those kind of multipliers, different sizes, or like, given this specific one single multiplier type, and then like how do we reduce the bits according to what we need?
So the question is, do we have multiple multipliers in a processor?
Different sizes. Like how do we know that we have 4 bits incoming or like 8 bits? And if we have 8 bits, how do we process it differently in a different place than if we have 4 bits?
All very good questions. So the question is, how for 4 bits, 5 bits, 6 bits, 7 bits, 13, 17, 113 bits in a processor, you know, you don't know what the users want. Maybe they want to add this or that and multiply this and that. Do I have different multipliers? Usually the question is, you end up having one big multiplier that can be maybe configured to do 2, like you can have a big 64-bit multiplier that can do 2 32-bit multiplications or 4 16-bit multiplications. Some people do that. In a lot of cases, actually, you have the same multiplier a couple of times, which is when we will see more advanced processor structures where you want to do more work. You realize that you want to have multi-issue processors. So while one multiplication is going on, you want to have a second one and a third one going in parallel. We will have all kinds of fun with these things, but it's not like it's a given. Part of the interesting part is to be able to create these things as it fits our purposes. So we are going to say, hey, in my circuit, I want to have, I frequently see different numbers. I want to have separate multipliers for these. Or you say, hey, I'm just going to reuse one big multiplier. Happens. There are also processors where they say, I don't want a multiplier. and I'll do the multiplication in software. Because it's the same operation you can also do. Hey, I AND things, I shift them, I add them, and you know, if you take 30 steps, you can do that. But 30 steps is, I mean, takes time. So that's also a trade-off you can make. If you're making a tiny, tiny microcontroller that has to fit into your ear or in your lungs or something like that, maybe you don't have the power, the size, the area to put it. Maybe you don't do multiplication so often. So why do I have to put into my processor a hardware for multiplication? It happens once every blue moon. If that happens, you say, I have a software routine. Yes?
Or is it an option to add like other multiplication for algorithms in hardware? Like we can make more efficient multiplication algorithms than the spread.
You mean like 4x4 or? Yeah, I mean, you realize what happens usually is you end up using a hardware and you realize what the strengths of the hardware are and you tune your algorithms to take more advantage of that. This is very common when you use, for example, GPUs, which can do certain type of operations better. And they can do certain algorithmic patterns more efficiently than others. So you spend, there are these translators that take a generic program and map it to the specific capabilities of the hardware underneath. That's a big thing these days, trying to close the gap so that the programmer doesn't have to know all the nitty-gritty details about how in hardware things were implemented so that you have some software support to do that. Big, big research question. Multipliers are done, so people are moving away. Okay, so it's completely okay. It's live, so you know. Operations based on adders. Now, very quickly, I will go over. Now we know how to add. We know how to multiply. We want to see some other operations, and these operations will be very practical. The first thing is negation. Remember how I use 2's complement numbers? I take A, I invert all the bits, and I add 1 to it. Somebody was asking, what do I do with this carry-in input? You know, it becomes handy because I need to sneak a 1 here, and inversion is, you know, I invert it, and this is an adder. And in comes A, becomes not A, add 1, I have minus A. I'm not saying anything, I didn't notice. That's okay. An incrementer is a circuit that adds 1 to the number whenever there is the need for it. So you have A, and you can sneak the increment from the carry in, and the output will be A plus increment. Wow, so great. And subtractor. Okay, I can have A plus minus B, and I know how to make minus B. I take B, I invert it, I sneak in the 1, I have the A, I add them together. Hey, the result is A minus B. Isn't that great? Now, you can get more creative and you say, what if I want to both add and subtract? Obviously, you can have this normal adder, the subtractor, and then you can put a multiplexer to choose, do I add, do I subtract, right? But not everybody likes multiplexers, so you can also do this. You can say, this is an XOR, so I can XOR B with the sub signal. So this is a 1-bit signal you apply to the entire vector. So if sub is 1, B will be negated. That's what XOR does. And sub goes in here, and A comes here. So this one can both add if sub is 0, or subtract if sub is 1. And all I had to do is add 1 set of XORs on the path of B and 1 signal. Like, we did 1 adder, but it's solving us multiple problems. Now, the best part is, and I'm not going to go into the details, just trust me when I say this, because it requires a little bit more discussion. If you can subtract 2 numbers and you look at the results, you can already make all the comparisons, right? If A is greater than B. If A is greater than B, the subtraction will be positive. So the number will have it on its most significant bit as 0. If A is smaller than B, the subtraction will be negative, meaning that the most significant bit will be 1. And you can look at it now. There are some strange things here, so please ignore them. But just trust me that the heart of the adder, or the heart of a subtractor, it's an adder, you make it a subtractor, and by comparing these two things with very little additional effort, these things, whatever they are, I'm not discussing them at the moment, are already inside the adder. There are some internal signals in some ways, which I might explain in another lecture. When I make the A minus B, I can figure out if they are equal, not equal, larger or equal, smaller or equal, very easily. That's a comparison, and that comparison will become essential when we are making our processors, because frequently you write programs, loops that have a clause that terminate. You say, if A something, do this, else do something else. What happens in the processor, he subtracts them, looks at the result, and based on that, he can make a decision. Okay, I'm hoping to keep the core group here. 540 students. 1, 2, 3, 4, 5. Okay, so not all arithmetic functions are realized by adders. There are some, these select ones, shift and rotate units, binary logic functions, and or XOR not. They are used in programming as well. These ones are very trivial to implement. Shift and rotate units are also sort of trivial. Now let's take a look at what shifters do. We have 3 different versions of them. So we have the, what's the order? Logical ones. We have the arithmetic ones. And we have the rotate functions. Now, the logical shifter, it's logical, makes a simple thing. You take a number, you shift it to right or left by a set amount, 1, 2, 3, 4, 5, whatever, and the empty spaces are filled with zeros. That's, you know, the logical way to do it. You shift it around, and you know, when you shift it around, when the number is like this, and you shift it this way, a couple of numbers fall off this side. And what do I do with these? I'll just put zeros. It's like the lazy man's job, right? Okay. Now, arithmetic shifters realize that if I'm modifying a number like this, and that number is maybe representing a 2's complement number or a real number, that maybe I shouldn't just replace it with zeros, and I should be careful when I'm shifting. So they are the same, but on the right shift, fills empty spaces with the old most significant bit. So it preserves the, let's say, polarity of the number. That's the difference between the arithmetic and the logic shift. Rotator, well, rotator is, remember the bits that I threw out? So I have the number, so there's 1 bit here, 1 bit here, 1 bit here, another one, another one. So if I say, hey, we are shifting this, it means that I'm pushing these bits. So the new bit is here. Logic, arithmetic, I filled it differently, okay. But there is this other bit that fell off. And in rotator, I take the bits that fell off and I insert them again on this side. Right? Boring? Okay. So here's the answer to the questions. In this case, this is the number. I shifted it right. So 110 became like this, and the empty spaces were filled with the black zeros. In the other case, I shifted it to the left. So 0, 0, 1 went all the way to the top, and then the empty space was filled with zeros. Good exam questions, by the way, you know, we will be asking things like that. So arithmetic shift, to differentiate it, I have 3 smaller, larger things. Now, in this case, I am shifting it to the right, meaning that this 1, 1, 0 will appear here. But instead of filling it with zeros, I look at the most significant bit here. It was a 1, and I keep on filling ones here. If I am going the other way, like this, I say, hey, okay, it's the same. I'm just going to fill by zeros. Yes?
Shifts have multiplication properties, but what is the rotator used for?
Shifts have multiplication and division properties, right? So you realize that if you shift a number to the this way, you multiply them. If you shift them this way, you divide them. Rotation doesn't have an arithmetic function, but it's a permutation of the number. And there are some cases where you want to use this. If you have a graphic game and you are scrolling things, you want the things maybe to come from the other side. Yes?
Why is there a left arithmetic shifter?
Why is there a left arithmetic shifter? You say because it's the same as a left logic shift. You are right, but it's just that when you are dealing with, I mean, you want to use arithmetic shifters when you're dealing with numbers, so that not to confuse people more and make the mistake, you say, hey, I have arithmetic shift operations and logical shift operations. And logical shift operations, you know that it will be filled with zeros. And arithmetic shift operations, you say, it will preserve the number. So it makes, in hardware, you will not make it differently. You will realize that, logical left shift and arithmetic left shift are the same. But to the user, you pretend like there are 2 different things. Good one. I think there's also a question here. Is such a comparator optimal, or should a comparator be implemented separately to optimize comparing, because we might not need the difference between the numbers? So the online question refers, sorry, I just saw it right now. It's this thing. Help. Just to answer the question, it's a good one. I might not need the entire adder. If you realize the way I'm drawing it, I'm already saying I will not need the A minus B, it's grayed out. So I will get rid of everything that I don't need. I build on an adder, I start with an adder, I do the operation that's necessary for comparison, whatever I want. Whatever I don't need, I'm just going to throw away. And it will get simplified. So the comparator will end up being simplified. Okay, we had our shifters. How do I design a shifter? Well, if you have a 4-bit vector coming in and you have a shift amount, and you can shift it by 0, 1, 2, 3 values, and out comes this, guess what will happen? Nothing very exciting, actually. We have our vector, and for each shift amount, I'm going to use a different multiplexer input. I told you, multiplexers. Totally underrated. As we were discussing a few seconds ago, a lift shift by n bits multiplies a number by 2 to the n. The same way that when you have a salary and your salary is written, I don't know, like this, 94,317, and you add 1 0 to it, you are richer. Okay, same way. You shift left by 2, you multiply it by 2. If you shift it by 2 digits, you get much, much richer. Okay? Now, arithmetic right shift, only arithmetic right shift by 2, by n, divides a number by 2 to the n. Those are special cases, meaning that making those calculations are easier than using a divider or a dedicated multiplier. So we sometimes take advantage of those things. Now, we also have, covered 90% of the operations that a regular CPU does. Most of the others, sometimes there is a division and square root unit inside a CPU. It's not that common. And exponential, logarithmic, trigonometric functions rarely have dedicated hardware, usually end up using numerical approximations, and mostly use lookup tables. Like for sine, you realize that you only need to sine up to 45 as a lookup table, or it's a combination of lookup tables and numerical approximations to fill in between. And as long as you have the right precision, so that you are not, I mean, the number of bits you calculate are correct, you don't really care. But 90% of what we want to do is already covered in this lecture. So what happens is we combine them in what we call the arithmetic logic unit. And the ALU, the arithmetic logic unit, is the reason why we study digital electronic circuits, because that is the only part of the CPU that does something that really means, that really moves data, transforms it, and makes something else. Everything else is Zeitisch, Nebengemüse. It just moves data around, brings data to the ALU, takes data from the ALU and brings somewhere else, handles exceptions, interrupts, whatever. And an ALU would look like this. So you have two inputs, usually, of n bits, 32, 64, whatever your thing is, and you would have a number of functions. In this case, this is the CPU we will be looking at, has 8 different functions it can implement, and to choose from 8 functions, it has 3 bits. Depending on those, on the function, if it's 0, 0, 0, I make A and B. If it's 0, 0, 1, I make A or B. If it's 0, 1, 0, I make A plus B. Somebody has decided on this encoding. Somebody said, you know what, these should be the functions. And it's the architect, the CPU architect, that comes up what type of operations should be there. And it's the instruction set architecture that tells you what encoding should be used. How we implement that is going to be another story. So we will cover these in the following weeks. Now, what is behind this thing? Well, what did you think? We have the multiplexer here. We have the AND unit, because at some point we have to do AND. We have the OR unit, because at some point we have to do OR. We have our adder, because I have to do addition. We have one more thing that, what does this guy do? Ja, was? Ach, komm schon. Scheiße. Inversion, right? He looks at it, and if it is 0, B comes true. If not, it is inverted by, it is inverted. And then the inverted one comes and is here, goes into the other, makes it a subtractor, and it comes out here. There is one strange thing happening here, and there is a carry out coming out from the other. But other than that, this looks very, very boring, simple, things that we could really, with our knowledge, build, write very low code for. And this is the heart of the CPU we are building. Yes?
Is there a reason why the 0, 1, 1 is not used?
0, 1, 1 not used. Good question. No, not used. The way they have constructed it, it doesn't create something useful. And they wanted 7 functions, not 8. So one of them was not bound to be used. They tried to figure things out. So for example, the addition and the subtraction are actually the same, 1, 0, 1, 0. And this bit just flips the inversion. So somebody did some sort of optimization there. It wasted one function. Okay. Now, there is one funny function, set less than, and set less than operation is one of the funny operations of the CPU we are looking at. And A is 25, B is 32. If A is less than B, we expect Y to be the 32-bit representation of 1. Okay, how do we do this? We subtract A from B, look at the most significant bit and extend it, 0 extended, meaning put 31 zeros in front of it, so that here I have a 32-bit number. And how does it go? Well, nothing very interesting. For SLT, we have to choose a function, meaning that I use 1 here, that inverts B. I use 1, 1 here, which corresponds to 3, so I use this output. So the output has become available here. And this is it. So the things that we are missing is there are some secrets about making adders faster. We obsessed a lot about it. I didn't talk about it. I'll see in the lecture schedule if we have time. I could go over it. In case there is also demand, we will definitely go over it. How can I make adders faster? We know how to add, subtract, multiply binary numbers. We see that the adders can be used for making subtractors, incrementers, comparators, and it becomes an important part of the multipliers. We know how other functions can be made, like shifting, and by combining all of them, an arithmetic logic unit can be constructed. Looks very simple, and it's not much more complex in any state-of-the-art processor. There are tricks, of course, and we will talk about some of them in the upcoming lectures. Next week, we leave combinational circuits for a while. We go back to the basics. We learn how we can store, memorize things. We learn how to divide operations into multiple time steps, and learn how to describe these sequential circuits in Verilog. That will complete the things that we can do, and that will allow us to build any digital circuit. Then we are ready to go. Thanks a lot. See you next week.
So it might be a dumb question, but for the exam, for example, like